Fundamental theorem of calculus part 2. It assumes that we have an antiderivative, and part 1 is saying what if Wolfram alpha can't find it, none of those professors know what the antiderivative is, and what's the situation here. And it says that it exists, but we can't really write it down in terms of sine, cosine, those functions. So here's the situation. So fundamental theorem of calculus part 1 states this. This part right here. And the situation is that we don't know what this capital F of x is, right? But if it exists, it must satisfy this condition. And how can we actually pull out this antiderivative? Is that actually playing with this index b. We don't play with this a, just keep it there. This is, we don't know, but if it exists, it must reveal by playing with this index b. So in the next slide, I think I changed that b to x and this integral variable x to anything else, right? That's okay. So you know that integral from 0 to 1 of f of x dx is absolutely equal to 0 to 1 of f of t dt, right? This is just a variable. You plug in 0 and 1 anyway, so it's going to be the same thing no matter what letter you use. It's dummy variable as long as there's this definite integral. So I switch the a and x and variable to something else because I use x for that. So fix a, and I change this, upper limit x to something else. Every time I change that number, it's going to pick up a different number, different area over different interval, right? So that's the idea of a function. If it ever exists antiderivative out there, we can capture that antiderivative which in the right-hand side we don't know, but it must be linked to this upper limit x in there. So they define a function like this. So I think that's the next slide. This is called signed area function. Let f be a continuous function in a to b, and c be some number in between there. If you consider this integral, because this function is continuous, this integral exists all the time. What theorem was that? Anybody remember? I named that theorem. Theorem of integrability of continuous function. Whenever the function is continuous, this number exists, no matter what two number you put it in there. So I don't change the c, but if I change this x, you will have different number every time. So right now, this capital F of x is not written capital F of x because it's antiderivative. It's just a letter I chose because it's linked to antiderivative later on. Right now, I just define a function in this way. This is called signed area function, or book usually say just an area function. So what is a variable of this function in here? Usual variable x. If I give you 5, you plug in 5 in there, get a number. If I give you 7, you plug in 7 in there, integrate and get a number. We don't know the antiderivative. How can you calculate this integral? You can't, exactly right? But you can do the Riemann sum, you can do whatever the approximation, you get a number out of it. But in our mind, conceptually, that number exists. Theorem of integrability of continuous function says the number exists whether it's computable or not. So I chose this function. This is a usual function that if you compose it like this, cosine and sine, we don't know the antiderivative. The antiderivative is not elementary. So I chose this one and define a function like that. X in here. If I plug whatever the number in, every time I get a number. So I think I have this little slide here to show you this value. Here, is it big enough? So in Mathematica, and I calculated, I changed the x beginning from negative pi, slightly higher, and slightly higher, and slightly higher. I chose various different values of x, right? All the way up to pi. The second entry here If you plug in those numbers, if you calculate this integral, you get this number, negative 0.6920. If you plug in negative 2.35 in place of x there, you get this number. So let me use this information, write that down. Please remain quiet. It distracts me a lot and other students as well. So until it reaches to 1050, remain quiet. Right here is f of negative 2.3561. According to that definition, you go here and plug in 0, and that earlier I chose 0. Then plug in that number, negative 2.3561. What was the function I chose? Just random function I chose like this, 2 pi sine of t dt, right? You integrate this one, and your question is, how can you integrate this one even if you don't know the antiderivative? How do you do that? Use Mathematica, or you use your Riemann sum and spend a lot of time, or go to Wolfram Alpha, integrate this one from 0 to whatever the number I gave you. Then it'll try and realize that it can't integrate, but it can integrate it numerically, and it's going to give you the number. So if you try this one 9 times with the 9 numbers, then you will get this value. X value, Y value, X value, and Y value. The procedure is numerically integrating it because we don't have antiderivative. But I hope it defines for you a function. I give you a number, numerically I get an output. That's a functional relation. It is just not elementary. Well, my point was that you hope you understand there is a function just defined, right? It's just barely just defined. We don't know it's continuous. We don't know it's differentiable. A function is just defined. I give you an x using technology or doing the Riemann sum. You can have an idea about what the output is. So here is a formal statement. This is the version, and here's what I usually say. No other version is accepted. This is it, verbatim, or is in the line of this one. This is the statement, which is wrong in here. This is supposed to be 1. Fundamental Theorem of Calculus, Part 1. We talked about it, never showed you the full statement. Here it is, right? So let's read it together. Function being continuous on that, so that integral exists, right? Definite integral exists. And C is a point inside there. Then we can always consider this x is inside the interval, c is inside the interval. Doesn't matter x equals c or x is less than c. This integral always exists, right? F is fixed. I change that number, x. Then here's a function. I call that capital F of x. At this stage is not antiderivative. It's just a function defined. The theorem says the f of x is differentiable. It implies it's continuous as well. Right, so you enter calculus. Function was barely defined. Here I'm claiming that function is differentiable. If it is differentiable, what's the derivative? And its derivative is inside function there. Therefore, capital F of x is, what is the statement said about capital F of x is what over little f of x? Antiderivative of little f of x. So it shows the existence of this function, input and output, right? But often is not computable. And they use this notation. There's no capital F of x, right? But if they write d dx in here, they're hoping that you recognize whatever is written here as a function of x. They didn't use capital F of x notation. They want you to understand what's in the box is actually a function of x. If I change x, this value is changing and it's well defined. Then you can put this d dx, right? All come together. So this result, if you replace the capital F of x with that, and it's stated like this. So this is how it's stated, and you have to know a statement like in this form. Continuous function, define what capital F of x is, area function. And conclusion says it is differentiable. Its derivative is that integrand function. Another thing you have to pay attention in here is the form. This one must be constant. And this one must be plain x, nothing else. x squared, nothing else. It doesn't work. It has to be exactly in that form. All right? That's the logic. This is exactly like that, and you have to put that in that and put it in the form. But what it really implies is that if you have continuous function, there is always antiderivative, right? Whether we can compute it or not, there is an antiderivative. And by sketching that yesterday's homework, I hope you saw the existence of that function. We just can't write it down in terms of functions we know. All right? Make sense? A statement asserts the existence of antiderivative, whether you're computable or not. Okay, here's one example of using part 1. It simply says antiderivative exists, and it is showing you kind of how the function is defined. So from there, and by sketching the graph from the homework problem, that you hope you see that existence. The function's out there. You have an x value and y value. But you don't have a formula for that. Right, so if you have this type of function defined, and I use g of x, and letting you know that this g of x is not an antiderivative of this inside function. All right, and this is more complicated here. So let me compare that with the fundamental theorem of calculus part 1. This function has constant in the lower limit of an integral, right? And upper limit, there's a plain x. It's not x squared or 2x or x minus 1, just simply x, right? And here's an integrand function. They're talking about this specific function. No other tweak is involved. But as you can see, here you have lower limit not constant, x squared, changing, upper limit also changing there, right? So it's not exactly the function they're talking about. So answer of this g prime of x is a little bit more involved. So if you know antiderivative of this 1 over 1 plus t to the fourth, then you can do it. And its antiderivative exists. If you use computer, it'll compute it. But I chose this one, so that you don't see that antiderivative easily. If this were t divided by 1 plus t squared, then you know it's antiderivative, right? Do you see the technique? Or fourth, I'm sorry. Anybody remember that? It was a little tricky one. Substitution with the t to the fourth doesn't work, right? It doesn't quite cancel. So we rewrote like this, remember? Then you enter arctan through the substitution. But it doesn't have t up there. So it's actually pretty difficult, right? But this is how it goes. Alright, g of x, and I use this g of x again, not capital F of x, and letting you know that g of x is not an antiderivative 1 over 1 plus t to the fourth. The book uses f of x, and you shouldn't think that that's the antiderivative, right? It's just a name for a function. So here, to avoid that confusion, I use g of x. So it starts like this. We don't know what an antiderivative is, but you know it exists, right? How do you know it exists? So inside function is little f of t, 1 over 1 plus t to the fourth. Right? By what theorem do you know is antiderivative exists? FTC part 1 that I just showed you, right? Part 2 assumes it exists, right? And part 1 says that it exists. So there it is, exists, right? Okay. Then how are you going to compute g of x? If you call that antiderivative f of t, not having a formula, just named it. Now you use this definite integral, right? So what is it? Bracket, right? That's how you calculate definite integral. Bracket. What's inside? Antiderivative, right? What is it? Capital F of t. We know it exists, it's ghost function, but we don't know what it is, but it exists there. And what is the lower limit here? X squared. Upper limit there, sine x. How about that? Treating x as a number. Any question? Then you plug this one in here, right? F of sine x minus f of x squared. Is that okay? It's a good point. So by fundamental theorem of part 1, right? Part 1 says there is an antiderivative, right? It has complicated formulation, but there is an antiderivative. Alright, how about next part? Is that okay? Writing gx in this form, using that ghost function, fb minus fa, right? Now it's asking you to compute the derivative, right? Here's the derivative. Then you're going to differentiate this one with respect to x, correct? Right. So think about capital F being cosine or sine. How do you differentiate this one? You differentiate capital F first, right? So that what happened to capital F? If this is an antiderivative, becomes little f, right? And then inside, sine x. It doesn't change. There's sine x in there. But something happened outside, right? What is it? Cosine x. What rule is this? Chain rule. Minus, you were doing the second term. Capital F is differentiated, so it's a little f, right? And inside, not 2x, is x squared, and multiply by 2x. We don't know what capital F of x is, but we know what little f of x is, right? Therefore, we can substitute back. So what is little f of x? It's 1 over 1 plus input raised to the 4th power, right? So it's 1 over, but we can put that cosine up there, divided by 1 plus sine raised to the 4th power. That's the first term. Does that make sense? Second term, your input is x squared, so 2x putting in the numerator there. I have 1 plus x to the 4th. Fair enough? That's the answer. There's nothing mysterious about this. Everything cosine x, sine x, and x to the 4th became explicit, right? Do you know what an antiderivative of this function is? Can you integrate the whole thing? That's this function right here. Right? We just differentiated, right? So what's the antiderivative of this one? The answer is this guy. Yeah. Okay. Now, how about g double prime of x? We don't need fundamental theorem or anything anymore. It's all session 2, right? Quotient rule and stuff. So I'll leave that as an exercise. Any question about this one? We can't calculate the formula of g, but we can calculate g prime and g double prime of x. Alright? So let me show you that picture again. That is the answer to the homework problem posted in Google Drive. Rather than just randomly choosing this point to sketch this function for which we don't have a formula, I think it's better. How do we sketch in the curve sketching session? How do we sketch the function? We looked at critical numbers, right? And then we looked at points of inflection, right? That's a better way than just randomly choosing a point. So you actually discover that point, discover that point, discover that point, and so on. How do you find critical numbers? That's right. You have this function, mysterious function. We don't have a formula. Now you take the derivative and set this one equal to 0 and see what value of x that equal to 0. And you differentiate one more time and set it equal to 0 and see where the point of inflection is. Then you can handle this type of thing a lot more efficient than randomly choosing x point and discover the shape. You go straight to that point, go straight to that point, and so on. Computing x value is immediate from there, but computing the y value of that, you actually have to do the Riemann sum or using the computer to get the value when you get the x value. But compared to randomly doing it, this is worth doing it. You have this important value, you go ahead and evaluate an accurate, that's better way of doing this thing. So it's one application of fundamental theorem of calculus part 1, going to showing this as a function like this. If I sketch it like this, you believe, oh, there is this function exists in front of my eyes. This is my existence, but we don't have a formula. All right? So this is a good application of really showing you that this function exists through the graph as you sketch it. All right. Is this application of a fundamental theorem of calculus part 1? Is this title make sense? What did I use? Anybody know how I used the fundamental theorem of calculus part 1? How did I actually use the theorem? When you're doing all that calculation, not knowing what f of t is, if it doesn't exist, this is old nonsense theory about a dragon, right? But it says it actually exists, so you can actually do this thing. It's not nonsense. That was it. All right, here's your moment. See if you can compute first derivative only here. It's your first exercise today. Use that ghost function f of t, capital F of t, to write cosine e to the t, antiderivative cosine e to the t, right? So it's your first exercise today. We're only calculating the first derivative. Second derivative is just derivative rule, and there's no fundamental theorem calculus involved or anything. Integral from 2x to ln x, cosine of e to the t and dt. The hint is that do not integrate cosine of e to the t. Remember in the earlier problem, I did not integrate that function 1 over 1 plus t to the 4th. I didn't integrate that. I just borrowed existence and were able to calculate g prime, not g. Yeah. So correction was made to that part, earlier part. If you have raised to 4th power, then it's going to be 8th power. Maybe that triggered the confusion. Yeah. Right. Okay. Thank you for pointing that out. So here, whole thing, input, must replace that in here. So that's why it went there in place of t there. And x is kept here. Hold 2x. It goes there, so that's the thing. All right? So that's the first derivative, and you can differentiate one more time using typical derivative rules. All right? Any question about this? Yes. Especially this part, try to be logical, right? Don't try to pick a pattern. Seems like he's putting that thing over there and here's the thing there. Okay, that's what I'm going to do. I'm sure it's going to fall apart in the test if you're not being logical. If you understand logic, it stays in shape, if not perfect. If you're just picking up the pattern and not paying attention to logic in the test, it just totally just break apart. But if you're being logical, again, if not perfect, you have, good thing going on, and I can sense that. All right? So try to understand the logic here. Any question? It's all right? So look at this problem here. Functions that are not elementary. There's this function, capital F of x. This is a function that we want to look at. This function is not elementary. This function, you cannot write it down solely in terms of, without integral, solely in terms of cosine, sine, or inverses of those, or e to the x, or square root, third root. This function is not in that realm, outside, but it exists. How are we going to sketch that? If it is not elementary, the best way to visualize this function is sketching the graph of the function, just like the homework problem. And here you try to do better than just randomly picking x values. So here is something we're going to do together to visualize this better. In terms of differentiating and all that, this is a lot easier because down there is a constant, right? Up there is a plain x. It's not sine x or x squared. So this is the exact function they're talking about in that fundamental theorem of calculus, part 1. All right? We're about to sketch it. So we compute critical numbers. We compute point of inflection. And at those points, we actually have to calculate this integral numerically. And you can nicely sketch the graph of this function. Right? So let's go ahead and compute the critical numbers first. But that was exercise number 2. Is that right? We're the second time doing this. So why don't we calculate f prime of x first? All right? Do not integrate cosine of e to the t. But you can still calculate f prime of x. In the earlier 2 problem, do you know why we did this complicated thing there? It's because the function defined has more complicated lower limit and more complicated upper limit. This is exactly fundamental theorem of calculus part 1. Constant, plain x up there, and whatever function in t. Then what is the answer, f prime of x? The answer is the integrand function with x in it instead of t. That's the answer. That's what the fundamental theorem of calculus part 1 says. Okay? And if you actually repeat what we just did, you get the same result actually. Because C0 is a constant. When you differentiate it, the minus part disappears. It's constant. Any question about this one? Alright? Now we know the derivative. Do you know with what part I'm going to do next? I have a derivative. What are we going to do? Looking at these questions here. Find critical numbers, right? Do you see the connection between critical numbers and f prime of x? What do you do with f prime of x to find critical numbers? Let me just do this for you. Anyone remember you set that equal to 0. You set the derivative equal to 0. Let me show you the picture again. That's a critical number, right? That's where the critical point is. That's where the derivative is 0. That's how we start curve sketching. All right. So we have derivative f prime of x, that number. We don't have a formula, but we have a derivative cosine of e to the x, right? Is that equal to 0? Do you know which angle in between 0 and 2 pi makes this cosine 0? Pi over 2, correct? One more? 3 pi over 2. Those are the 90 degree and 270 degree. X coordinate there on the unicircle is 0. That's why cosine is 0. But what is this equal to? Is e to the x. Inside the cosine x, right? That e to the x must be this angle. But it can go more than just between 0 and 2 pi. So it all happens with this period, integer multiple of 2k pi. As k varies from 0, 1, negative 1, and 2 and negative 2, this will generate lots of numbers, right? All those numbers, if they go inside cosine, is a 0. But inside the cosine is e to the x. So what happens if you solve that for x? ln of pi over 2 plus 2k pi, right? And here's ln 3 pi over 2 plus 2k pi. Now if you vary this k from 0, 1, negative 1, and negative 2, and so on, x will be generated, right? If this is negative 5 or something, this is a negative number, ln is not defined. So, but as long as the k is positive, this will generate a number, but we only want those critical numbers in between 0 and 2, for example. Okay? Then you have to choose vary this k until you hit that number in between 0 and 2. So I did that. So here, you can use a calculator. You plug in k equals 0, k equals 1, and k equals 2, and k equals 3. I generate a number 0.45. 2.06 is outside interval, right? So only 0.45 works. In the second kind, 3 pi over 2. And I change this 0 and 1 and 2. Use a calculator. Then I have 1.55 generated. Next number is 2.39. It's too big, outside the interval. So these are the two critical numbers. After you go through all these k values, anything that fall in between the 0 and 2 is these two numbers. 0.45 roughly, 1.55. That's where it takes place, in between 0 and 2. Very good. That's the critical numbers, right? How do you know the critical numbers are local maximum and minimum? What test do we use? Second derivative test, right? If it is a positive second derivative, what is the conclusion? Local minimum. Thank you. If it's a negative second derivative, it's concave down, it's local maximum, right? So let's find, so that's the answer to part 1. Compute all the critical numbers. There are two numbers, a 0.545 and 1.55. Make sense? So let's see if this is correspond to local maximum, local minimum. So how does that part go? Compute the second derivative, right? So here's the second derivative. What's the second derivative? You apply derivative rule here. That's the first derivative, right? You see that negative sine x, sine of e to the x. What do you multiply? Derivative of this one. I have to multiply something out there, right? What is it? E to the x. Fair enough? That's the second derivative. Okay. Then what do we do with the second derivative? Plug those number 4, 5 in here. So f double prime of 0.45 is a negative sine of e to the 0.45 times e to the 0.45, right? All we care about whether it's a positive or negative. Turns out it's a negative number. If you plug this one into the calculator, it gives you a negative number. So, conclusion? Local max at where? At x equals 0.45. Alright? So it looks like that. That's what's happening around 0.45. How about the second one? F double prime of 1.55. Then it's a negative sine of e to the 1.55 multiplied by e to the 1.55. This is always positive. Doesn't affect the sign of this value. Turns out it's a positive. This went over the limit, so negative become positive. So we have local minimum at where? X equals 1.55. Right? So that's this part. Use a second derivative test to determine whether this is local maximum, local minimum at those two critical points in between 0 and 2. Right? Okay, that answers part 2. Next thing we do when you sketch a curve is finding a point of inflection, right? What do we do to find a point of inflection? Right, you set the second derivative equal to 0, right? So here's the second derivative, which is negative sine e to the x, right? Times e to the, you set that equal to 0. Then it's a product of two things. Then it actually it is two equations. Negative sine of e to the x is 0, or e to the x is 0. Right? Product of two things set equal to 0. Each of the factors is 0. Gives you two possibilities. So this one, e to the x will never hit 0. E to the x is always a positive. So there is no solution to that part. It is only coming from, if you multiply negative, we have sine of e to the x being 0. Do you know which angles gives 0 value of sine in between 0 and 2 pi? 0 works, and next one, 180 pi, right? And then you add 2k pi. Then it can happen over this period of 2k. So this is supposed to be not x, what's inside the sine x, right? That e to the x must be these values. Perfectly logical. Then how do you solve that for x? Put ln in there, right? So ln of 2k pi, or ln of pi plus 2k pi. Now you vary all these k values until you get numbers in between 0 and 2. So I did that in here, log of pi plus all that, and it includes 0 as well. So it turns out these are the two numbers, 1.14, 1.83. And after that, it is outside 2, so we do not collect that. So we have these two values here. These are potentially point of inflection. Second derivative definitely 0. You can actually use a third derivative test. If you differentiate one more time, if you plug in these numbers, if they are actually positive or negative, it means it's changing sign. Therefore, it's a point of inflection. However, when you sketch this one, you can easily see that it must change because it's concave up and concave down and things like that. So we have four numbers, two critical numbers, 2 point of inflection. Next thing we have to do is that you plug in these x values to our original formula here and use technology to calculate the actual function value. This is the hard part, so we have to use the machine. And then I did that, and I think I have the numbers here. 0.45, 1.55, 1.14, 1.18. Those are the four numbers, right? So I copy that. Using this integral formulation, for which we don't know the antiderivative, these two are critical points. These two are where potentially point of it changes. So I'm going to go ahead and plot this one, x here and y there, the graph of this f of x. And if you plug in x equals 0, that's quite easy, right? Integral 0 to 0, that's 0 here, right? And here's 1, and here's a 2. First one, 0.45, was roughly 0.13, so it's a fairly small number in here. And that was local maximum, right? So it looks like that. Next critical number was 1.55, so it's roughly about there, but it is lower and negative number. That's the function value when you plug it in there. That was local minimum. And where's point of inflection? It's concavity change, 1.14, it's roughly around there. And its function value is down here, 0.25, negative 0.25. And at the end, 1.83, it also changes there as well. And that was a little lower here. So I guess it remains concave up like this. And here, at the last moment, it changes to concave down. And here, that remains concave down, and this is where concavity changes and heading to 0 like that. So this is a graph you can sketch just using 1, 2, 3, 4, 5. We revealed the very accurate shape, and we have confidence nothing crazy is going on in between these two values. All right, so I think I have a picture of actually computer-generated picture. Computer actually go through thousands of points in between 0 and 2, calculate that integral using approximation and some sort of Riemann sum, and plotted all that points. Right? It actually takes some tens of seconds for a computer just to generate this picture. If you use a TI-80 something, it takes like a minute or two. It does very slowly. It's a difficult calculation. All right? So that's one application of fundamental theorem of calculus part 1. You don't have antiderivative, you can still bring this to existence. The function we're talking about, f of x, the antiderivative of cosine of e to the t, is this one right here. We just don't have a formula. Okay? So I'm going to go through the proof of